Now I would like to consider the automorphic correction for holomorphic Jacobi form. Let phi be holomorphic Jacobi form of weight k and index m. First of all, if I write down the Taylor expansion of this function, or maybe I remind you first of all the Fourier expansion of this function, then n is non-negative, and for n m minus L to the square is always non-negative. So the hyperbolic norm of the index of all non-zero Fourier coefficients are non-negative. Then how we can write down its Taylor expansion? First of all, for the function f0, we have the following Fourier expansion. This is the sum of all non-negative n, then the sum of all L in Z, such that for n m minus L to the square is greater or equal to 0. So for a fixed n, we have only finite sum a n L q to the power n. This is the function f0 plus so on. But if we try to find, so maybe I fix this here, this is f0 in tau. Maybe here we add also the Taylor expansion of this function, f n in tau, z to the power n, n greater or equal to 0. Now, if we try to find the Fourier expansion of this function, what we get? First of all, if we analyze the Taylor expansion of any term in the Fourier expansion, then here we have z to a positive power only if L is non-zero. But then n is strictly positive. So I don't like to write down, it's possible to do, but I don't like to write down the Fourier expansion explicitly. But we know that we have no constant term in the Fourier expansion of the Taylor coefficient fn. Bn q to the power n, n is strictly positive. So now I would like to analyze the function of the automorphic correction of our holomorphic Jacobi form. So e to the power minus 8p to the square m g twin tau z to the square phi to that is equal to the sum g n in tau z to the power n, n greater or equal to 0. So we see that in many cases this function are cusp form. Now I would like to describe all these cases. For example, if our function phi is a Jacobi cusp form, then all this function will be certainly cusp form, because here the first function f0 will be cusp form. But now I can formulate a better corollary. Now the first corollary was about weak Jacobi form, but the second about holomorphic Jacobi form. Corollary 2. Phi is holomorphic Jacobi form of weight k and index m. Then all function, all Taylor coefficients of the automorphic corrections will be cusp forms of weight k plus n if the constant term of the Taylor expansion of our function is a cusp form of weight k, or if this function is identically 0. Certainly, if we have this property, in all other Taylor coefficients of function phi, we have no constant term, and then in this product, we'll have no constant term in all Taylor coefficients. It gives us the next corollary. It's very simple, but useful in many considerations. So this is not explicit formula for the dimension. Explicit formula you can get using the Riemann-Roch formula. I gave you a reference to a recent Freitag paper on this subject. But here we have the following elementary estimation. You can find this estimation also in the Eichler-Zagier book. Then this dimension is small or equal to the dimension of the space of all modular form of weight k. Let us assume that k is even, plus the sum of the dimensions of the space of parabolic modular form of weight k plus 2e, summation from 0 till m. So this is application of automorphic correction to the classical theory of Jacobi forms in one variable. So you see that automorphic correction is very, very useful. But the next step is to use the same idea in the case of Jacobi forms in several variables. So our next step is automorphic correction of Jacobi modular forms in many variables. In this case, our method gives us very, very nice result. First of all, I would like to use to fix the setup for this method. Phi will be holomorphic or weak, doesn't matter, Jacobi form of weight k and index L, or for lattice L. So we can consider holomorphic or weak. It's two different cases. Jacobi form. So then V is a non-zero vector in L. And L1 will be the orthogonal complement of V in L. This is some lattice of co-rank 1 in L. Now we can write arbitrary complex vector in the complexification of the lattice L as a sum, orthogonal sum, of two vectors, Z1 and usual Z times V, where calligraphic Z1 is a complex vector in the orthogonal complement, and Z is an arbitrary complex number. Now we are ready to write the automorphic correction of any Jacobi form in many variables.